Hi friends, welcome to Gatematic Education. This is Santosh Kumar. Today we are going to start Root Locus. So till now we completed 3 units and I hope that you people started practicing. Now you know after 2 mirror discussions, now you know what is the importance of practice, right? But the importance of practice with ATM. Okay, so we are going to start Root Locus today. What is the purpose of root locus? First we'll see that the root locus purpose. Wait a minute. The first point, to find the closed loop system stability. Why we are doing all these discussions? We started our journey for the stability find out from the RH criteria, isn't it? The first thing is RH criteria, okay? Then we are going to discuss this root locus, correct? Then we'll discuss the Bode plot, okay, Nyquist and polar plots, okay. So these all techniques are to find out the system stability. So till now we completed the RH criteria. In the RH criteria, for the stability we consider the characteristic equation, that is 1 plus GA such as 0. Okay, so for this only, the RH criteria, we consider the characteristic equation to find out the system stability, but remaining all these techniques we use open loop transfer function. The open loop transfer function is always given by GSHS. When HS is unity feedback, then it's simply GS, correct? HS equal to 1 over here. Okay friends, so all these techniques, root locus, Bode plot and Nyquist plot and polar plot, we are going to discuss the stability only, but for the closed loop system. Okay, for all these cases we are finding the closed loop system stability, okay, but the procedure is different. For the root RH criteria, we are taking characteristic equation in consideration. For all these 3 techniques, we are considering open loop transfer function. Now you people will be having doubt maybe that, sir, if you are finding out the closed loop system stability, why we are considering open loop transfer function? Friends, there is a magic. We'll discuss about that. Let's come to the second point, and the second point says, let me clear some parts. To find the range of K value for the system stability and marginal stability. This thing we did in the RH criteria also, isn't it? The next one is to find the natural frequency of oscillation. Definitely we'll find out the omega n. We'll find the value of K for system stability and marginal stability. What will be the range? Conditional stable means, correct? Now the next one is to find the K value for undamped system. What is the undamped system, friends? Zeta will be in the range of 0 to 1. I'm extremely sorry, this is for this one. And for undamped, zeta should be equal to 0. For overdamped, zeta should be greater than 1. And for the critically damped system, zeta is exactly equal to 1. Okay, so we'll find out this K value for these 4 things. Okay, the next one is to find the relative stability, as we did in the RH criteria also. If you remember, our last topic was relative stability only. So the best method to find out the relative stability is root locus. Please remember always, the best method to find out the root locus, the best method to find out the relative stability is root locus, but the best method to find out the absolute stability is the RH criteria. What is the absolute? In the absolute stability, we can directly come with the conclusion that the system is stable or not. As we have seen in the column, the first column of the RH table, we can analyze all this. Let me take C1, C2, C3, all the coefficients of the first column. If there is a no sign change, I can directly conclude the system is stable system. If there is a sign change, the system will be definitely unstable system. So directly I can come to the conclusion the system is stable or not. So RH criteria is best suited for the absolute stability, and the root locus is best for the relative stability. Okay friends, so I think it will be clear to you. Now our topic name is root locus. Root locus. So what is this root and what is the mean by locus? Wait a minute. So here we go. Root means roots of characteristic equation. Root means roots of characteristic equation. The characteristic equation's roots is nothing but the closed loop poles. Isn't it? See, if you have this is your open loop transfer function, suppose, or let's take the forward path gain GS. What will be the closed loop if the unity feedback is given? It will be KNS divided by GS 1 plus KNS divided by GS. So finally KNS divided by 1 plus G of S N of S. This is nothing but the characteristic equation. So the characteristic equation is nothing but the poles of closed loop control system. This is the closed loop control system, isn't it? So root means roots of characteristic equation only. Okay, that's why we are considering this is the analysis in which we are doing the stability test for the closed loop control system. What is the path? Locus. Locus means path. Locus means a path, how your roots are moving. Okay. Now the root locus means closed loop poles path by varying k from 0 to infinity. Okay, we'll learn about this, don't worry. So locus you understand, root you understand. It's kind of, suppose you started your journey from your home and you are going somewhere. Let's take you are going Delhi. Okay, so you are following some path and you are reaching to Delhi, isn't it? So this your entire journey, this path is nothing but your locus. And who is the root? You are the root. Okay, enjoy. This is your new name now, root. So root locus means closed loop. So in control system, the root locus means closed loop poles path by varying k from 0 to infinity. We'll see how we are varying k and how it is the path of closed loop control system. By the common sense we can say, definitely if we are going to discuss about the root locus, means we are going to discuss about the closed loop poles only. Why? Because we are dealing with the closed loop control system stability only. Okay friends, so this is all about this. Let's start the root locus. Now what is the inside? Okay, so this is given over here, the first order system type 1 system, isn't it? Now the question is, find out the root locus or draw the root locus to the following system. The question is, draw the root locus. So we just discussed about root of what? Root of characteristic equation, isn't it? So what is the characteristic equation for this? 1 plus GSHS. Is it okay? So 1 plus K by S, HS is 1 over here, equal to 0. So finally you are getting S plus K equal to 0. So what is your S? S is your nothing but your root. So S is equal to minus K. So the root is depending on the K values, isn't it? Means if I'll choose here K value, I'll take over here S values. This is nothing but your root. And we are going to discuss the path of this or locus of this root by varying the K values, isn't it? Now if we'll take K equal to 0, it will be 0. K equal to minus 1, it will be minus 1. Like this up to infinity. Up to infinity, it will be infinity, minus of infinity, isn't it? Your K value is 1 over here. 1, 2, 3, it will be minus. -1, -2 and all. So this is nothing but your path. So this path, if I'll draw it on the ace plane, how it will come? This is the ace plane. Your ace values are 0, -1, -2. So this is 0. Okay, we represents, sorry, this is this sign is for the pole, correct? For 0, we'll draw the circle. Okay, so this is at 0, then -1, then -2, then -3, like this. If the k value is going to increase, this is nothing but your path, isn't it? Here I'm considering integer values only, but it is 0.1, 0.2. So this is the continuous root of the given system. Here the k value is 0. Here the k value is infinity, isn't it? Means for this particular system, the root locus means how the root is moving. It's starting at s equal to 0 and terminating at s equal to -infinity. Okay, so this is my root. So over here, you people are thinking, earlier I told you people that for the root locus, Bode plot, Nyquist plot and polar plot, we'll consider only the open loop transfer function. But here I'm showing you the characteristic equation. Why? The question is why? See, just wait and watch. Everything will be clear. What is my point? My point is, suppose instead of the first order, now you have GS for the same system. Whatever we discussed here, now GS is k by s square. So if you'll make the characteristic equation for this, we'll get s square plus k equal to 0. So for this, find out the root value, means ace value. Ace value is nothing but plus minus k under root k into j. Okay, now again your ace value is depending on the k. You can vary the k, you can get the different values of your pole. Okay, or instead of pole, I'll say over here the root of the characteristic equation is nothing but the pole of closed loop control system. So over here your poles are moving on the imaginary axis only. There is no real part you can see over here. So k is 0, you will get your poles over here. If k is in C positive, so it will come over here. Like this your poles are moving in both the directions. Like this you are moving. So this is your path. This is your root locus, entire imaginary axis. Okay, you can do the same thing if your GS is k is cube kind of. So for this particular thing, it's easy to draw the graph. But if the order increases, it's a very difficult task to draw this graph directly, or this diagram root locus path directly. Okay. So the note point is, if the order increases, okay, suppose you have equation s to the power 8 plus 3s square plus this equal to 0. How will you find this roots? There are 8 roots. Can you do this? It's very difficult to find out. That's why please note this point first. As order increases, finding the roots for equation is very difficult. Hence, we cannot draw the root locus. Okay. Here you have only 2 roots. Here you have only 3 roots. So directly we are, finding or drawing this root locus path, root locus diagram. But if your order will increase, it's very difficult to find out. Okay. So very difficult. Hence we cannot draw the root locus diagram by using characteristic equation. Okay. So in the new technique, this technique we are going to discuss in the root locus chapter, we will use the open loop transfer function, means GSHS, for analysis. But in actual analysis, the actual analysis will be done by the closed loop poles only. Isn't it? What it means, I'll tell you later. So friends, it's kind of, if I'll take the real time example, so I'll take, it's kind of runner. In the cricket, if we get injured, we can take the runner. Okay, according to ICC rules, it is not possible, but initially it was the rule. If you are injured, you can take the runner. So in actual, you were betting on the crease, not your runner. Your runner was taking the runs for you only, isn't it? So the same thing is here also. For the analysis of root locus, we will consider the open loop transfer function only, but in actual the analysis will be done for the closed loop poles or the closed loop system. Okay, now mathematically we'll see how is it possible. Okay, so let's come over here. So there should be relation between open loop transfer function and closed loop transfer function. So here is the heading, the relationship between open loop and closed loop transfer function, poles and zeros. There should be relation between them. If you are using open loop transfer function for the study, but in actual you are studying for the closed loop transfer function, so what is the relation in between them? Okay, we need to know about this. So let me start now. Let me change the pen. Open loop transfer function. Open loop transfer function. Open loop transfer function is given by GSHS. Let's take this is in the form of numerator and denominator. I'm taking this is the form equation 1 I'm giving. Okay, numerator some A's terms, denominator some A's terms. So this is in general I'm taking open loop transfer function. Okay, so what are the poles of open loop transfer function? This one only, means you will equate this ds equal to 0. So what you will get? You will get poles of open loop transfer function, isn't it? Now what about ns? The numerator terms, if will equate to 0, so these are the zeros of open loop transfer function. Okay friends, now if you will find out the characteristic equation. Characteristic equation denotes the poles of closed loop system. We have seen this and you have to remember if you forget about this. Okay, so friends, I'll write over here the closed loop are given by the characteristic equation only. Okay, so what is the characteristic equation? 1 plus g of s h of s equal to 0. This is characteristic equation. The characteristic equation is nothing but the poles of closed loop system. And why I'm considering the poles of closed loop system? Because the closed loop system stability we have seen for the poles only, means the poles are deciding factor for the stability. We have seen earlier, if your poles are in LHS, then system is stable. If your poles are in the RHS of S plane or the positive real, your system was unstable. So have we discussed about zeros? No, not yet. Okay, so the stability of closed loop transfer function we can identify by the closed loop poles only. That's why I'm considering over here the characteristic equation. So now let's put these values, k and s by ds equal to 0. Perfectly fine. Now finally you have ds plus kns equal to 0. This will go to 0 and you are remained with this. This is nothing but the closed loop poles, isn't it? Now the closed loop poles comprised by, what is this? This is, let's take equation A, let's take equation B. So this is nothing but A. A is nothing but the poles of open loop transfer function. Your ns is B, means your zeros of open loop transfer function. So there is a relation. Your closed loop transfer function is nothing but your open loop poles and your open loop zeros, isn't it? See over here, the closed loop poles comprised by the open loop zeros and poles, isn't it, friends? Now I'll take this on the next, that is equation was ds plus kns equal to 0. Okay, now over here let's take k equal to 0. If you'll take k equal to 0, what it means in this equation, let's take this as equation 1. In this equation put the k equal to 0. What you will get ds equal to 0, and this equation will be intact. This is nothing but the closed loop poles. So this is the closed loop poles, isn't it? In this equation, if you'll put k equal to 0, you will get ds equal to 0, and this ds is nothing but, if you remember, this ds is nothing but the open loop poles, the point A, or I'll write over here open loop poles. So for k equal to 0, for the k equal to 0, your open loop poles become closed loop poles. Here is the relation. So what I'm going to do, I'm studying the open loop poles and zeros only, but indirectly I'm analyzing the closed loop poles. Why? Because there is a relation. At k equal to 0, the closed loop poles are equal to open loop poles, isn't it? Now if you'll consider k equal to infinity, then what will happen? So if k equal to infinity over here, in this case you will get ns equal to 0. Infinity you can write 1 by 0. 0 will multiply with ds, so will remain with ns equal to 0. So this is nothing but your closed loop poles always, because this is the equation 1, closed loop poles. In that equation you put k equal to infinity, you will get ns equal to 0, and ns is nothing but the open loop zeros. Open loop zeros, isn't it? Because open loop transfer function we have seen there, k ns by ds. Okay, so here it was the pole, open loop pole ds, and ns was nothing but the open loop zeros. So at k equal to infinity, the closed loop poles is nothing but the open loop zeros. At k equal to 0, your closed loop poles is nothing but the open loop poles. Okay, let me take the pen. Very, very important, these 2 points. One is this, means if your poles, what is the condition? This is your poles at k equal to 0. Poles of what? Poles of open loop control system. So it will move like this, it's moving continuously up to infinity, k equal to infinity. So this is the path of your open loop parameters. What I mean is, at k equal to 0, this is nothing but the open loop poles, which is equal to the closed loop poles. Similarly over here, this is the open loop zeros, and which is equal to closed loop poles. Means overall for k equal to 0 to infinity, your poles are moving. The poles are what? The closed loop poles. The closed loop poles are moving. So if you are studying the closed loop poles, it means you are studying the closed loop stability, isn't it? So is this clear to you? So this was the introduction part of the root locus. In the next lecture we'll discuss something more about this. Okay friends, so for the new updates you can subscribe, and you can find us on the Facebook for the doubt solving. We'll meet in the next lecture. Till then, take care and bye.